Hello everyone, you are so lucky to have found this video because today we're going to be talking about different ways to represent coordinates in 3 dimensions. That's right, there's 3 dimensions now. If we take our original x and y axes that lived in the plane, we can now extend into the 3rd dimension, our z-axis, which points up like this. We can now describe points in space as an ordered triplet. X, Y, and Z. The x-coordinate tells us kind of how far over we've gone on the x-axis. So we can draw a little dotted line down here to project where the point casts a shadow on the plane. And the x-coordinate is how far along this axis it's gone. On the y-axis, we can do something similar and look how far over in that direction it's gone. And then we can trace it up. How far up did we go would be our coordinate z. Now, this is great. We can now describe where something is in 3D space. But it turns out there are ways that are more efficient or more clean to describe the same points. We're going to find as we start doing multiple integrals or look at geometry in 3 dimensions that the traditional x, y, and z coordinates create functions that look really messy, that make our work more difficult or often even impossible to solve without going to these new coordinate systems. So how can we do that? What is a different and more efficient way to describe this same point? Well, one way, as we have hinted here already, is the cylindrical coordinate system. Whereas Cartesian coordinates look at x, y, and z, we're now going to look at how far we are from the origin. So we kind of look at where that shadow is casted down onto the plane, and we call this distance a radial r. We can also look at some angle as measured from the x-axis, and we call that theta. Then we look at z. Z doesn't really change in cylindrical coordinates. And so what we really have here is what's called the polar expression, a distance out from the origin, sweeping along from some angle from the x-axis, and then we kind of move that point up or down along the z-axis. So cylindrical coordinates are really just polar coordinates, which you may have already learned, plus a z-coordinate, how high above or below you are from the xy plane. Most of the relationships between Cartesian and cylindrical coordinates are what you already know how to do from doing polar. So if we have x, y, z in Cartesian, we can now do polar coordinates as that distance r. We can look at that angle theta from the x-axis, and then we just go up or down some distance z. So we have x, y, z is what we're used to. Now we're going to go to cylindrical land where we have r, theta, and z. If we want to convert between these two frames of reference, we'll use our normal polar expansions. X is going to be r times the cosine of theta. If we look down in the plane, hey, look, it's 2D again. We have some point here that's some distance x over and some distance y up, but it's some distance r directly from the origin. This x component here is just the side of the triangle that forms that's adjacent here, so we use cosine. The y side of that triangle is going to be y. It's the opposite side, so we use the sine of the angle to make that one work. Z, you ready for this? It's just z. There's no transformation. Whatever number value your Cartesian z was at, your polar or your cylindrical z is going to be at as well. There's no change there. So really, you're just converting x and y to polar, and then you're allowing that shape to go up or down into the vaster regions of space. If we want to go the other way, if we have the information in x and y and want to get to our new polar expression, we can use the fact that r is the hypotenuse of this right triangle here. So it follows the Pythagorean theorem that r squared is equal to x squared plus y squared. You really want to look for this expression in your functions in the future, because you can turn any widespread x squared plus y squared into a single valued r squared. Likewise, this angle here can be measured in terms of the opposite y height of the triangle and the adjacent x side of the triangle. And we can get that the tangent of that angle is just the y over the x, the opposite over the adjacent. So these are our polar identities, and we get z for free just to make it cylindrical. So we can take some really ugly looking expressions and turn them into a much nicer looking thing for cylindrical coordinates. For example, if I want to look at the equation x squared plus y squared equals 9, well, we know from what this looks like, this is going to be a circle of radius 3. Right, we have x squared plus y squared equals a squared. That's 9. Square root of that is 3. And so if we turn this into polar coordinates, this x squared plus y squared I told you to look at just turns into an r squared, and that means that the right-hand side is 9. If we root both sides of this, we get r equals 3. So this is a circle of radius 3. But wait, a circle's a 2D shape. We want to be looking at things in 3 dimensions now. Well, if we are under the assumption that we're working with cylindrical coordinates, this expression here represents all of the points in space that are a distance of 3 from the origin. So really, it's not so much a circle of radius 3 as it is a cylinder of radius 3. If we were to plot this, we would have our circle in the plane, and then we would just kind of extrude that up and down infinitely, as high as it can possibly go and as low as it can possibly go. So this is the set of all points of radius 3. This is a cylinder. Kind of, if there's no z in the expression, you're assuming that you're working with all z. You can take whatever shape you have in polar expression and extrude that up and down into the third dimension. It even works for more interesting polar shapes. For example, r equals 1 plus cosine theta gives us a kind of unusual shape called a cardioid. The cardi gives us, meaning heart-shaped. If we plot this in the xy plane, it makes this kind of cute little heart with a long side down the x-axis and the little lobes going onto the other end of the plane. Well, if we are assuming that we're working in 3D, now we can take this heart shape, like it's kind of a little cutout for Play-Doh, and we can draw a 3-dimensional shape above and below that represents kind of a prism that is the cardioid shape. You trace out the little path in the plane, and then you just take that up or down to give all of the points in space that satisfy the polar equation. So we can just extrude the polar shape above and below the plane. So there's our cute little heart. Other shapes we can describe very nicely with cylindrical coordinates. For example, if I just have z, some function z, some height I'm looking at, equals x squared plus y squared. Again, the right-hand side tells us circles, but the actual radius of the circle is going to depend on how high we are. So what happens is the right-hand side can really never be negative for real numbers. And so we get at 0, x0 is 0 and y is 0. And then as x and y start getting larger, z is going to help give us circles of different radius, and radii even. And what we trace out is kind of this bowl shape. If I have x is equal to 0, then in the zy plane, we get a parabola, z equals y squared. If y is equal to 0, we get another parabola spanning the x-axis. So it kind of goes this way and up along that. So we have a parabola going this way in the zx plane. We have a parabola going this way in the zy plane. If we want to put that together to create the actual surface that's formed, we can draw a circle around to kind of connect those four curves, and we end up with this sort of weird bowl shape. This is called a paraboloid. It's a shape made from a bunch of parabolas. And so this is another kind of shape that we can build in 3 dimensions. In Cartesian coordinates, it's ugly, but we can always replace this x squared plus y squared with a nice simple r squared, and that is much cleaner to have just the equation z equals r squared. It's a very simple way to express this more complicated shape. We can take other expressions. 16x squared plus 16y squared equals 25. I notice I have the coefficient 16 on each of my variables here. I can divide through, and I get my friend x squared plus y squared again, which means I can replace that with an r squared. And now my right-hand side, which is conveniently all made of squares, I can square root both sides, and now I get this circular cylinder with radius 5/4. So again, a really nice way to clean or to express what is sort of a messy expression otherwise. Y, when you write this, doesn't really even create a function for a circle. You have that upper part and then the minus part from the square root you would get. Here, I just get r equals 5/4. It's a nice little expression that we can get. So the other thing we might want to be able to do is be able to convert back and forth between Cartesian and cylindrical and vice versa. So imagine I have the point defined in Cartesian coordinates as 1, 3, -2. I want to convert to cylindrical. Well, I have x, y, and z. I need to convert using these 3 values. I need to get to something in terms of r, theta, and z. So let's do r first. We have x and y. These are the legs of a right triangle with r as the hypotenuse. So r is going to be the square root of x squared plus y squared. Our numbers here are 1 and 3, so we get 1 plus 3 squared is 9. So the whole thing is a radius of root 10. For the angle, we use the expression that tan theta is y over x, which means I have 3 over 1 as the ratio there. I do theta is now the arctangent, or inverse tangent, if you like it that way better, of 3. If I put that into my calculator, it tells me that this angle is equal to about 1.25 radians, or if you're a degrees person, 71.6 degrees, more or less. So we've got 2 coordinates. We've got r, we've got theta. Now we've got the really hard one. We've got to get z. And look, z is -2. It stays -2 in cylindrical as well. So we're done. R, this point P in cylindrical coordinates is going to be written as root 10 for r. We have 1.25 radians for theta. And then z is just the -2 we were given in the beginning. So that is our point there. We can also go the other way. So maybe I start with a point already in cylindrical with a radius of 4, r, an angle of pi over 6, theta, and a z coordinate of 3. I want to be able to go back and get this into the form of x, y, z. So now we use the other expressions. I use my r and my thetas to get the x and the y components of this point, respectively, by doing x equals r cosine theta and y equals r sine theta. R is 4, cosine of pi over 6 is root 3 over 2. So we get 2 root 3 for our x coordinate. Sine of pi over 6 is just a half, so that gets us a nice 2. And then z gets to just stay z as 3. So that was nice and simple. So putting it all together, our x, y, and z coordinates are going to be 2 root 3, comma, 2, comma, 3. Not a lot of variety in numbers there, but that's what we got. All right, so that's cylindrical. We did it. That's all the ways to express coordinates in 3 dimensions, right? Absolutely not. There is a different coordinate system that is useful for certain symmetric systems that is based not off a cylinder, but instead a sphere. So now we're going to look at the spherical coordinate system and see what that is all about. We're going to describe 3 new coordinates. We have rho. It looks like a curly P, but is in fact a Greek R, a rho. That's R-H-O, by the way. This describes a distance from the origin again. But instead of being confined to the plane, it points directly to whatever point happens to be in 3D space. We have a new angle, phi, which is an angle down from the positive z-axis. And then lastly, we can't keep away from him, it's our traditional theta. This is the same theta that you would see in polar and cylindrical coordinates. It is the angle from the positive x-axis that swoops around. So if we're looking at a point in space, same thing. There's our point, just to kind of show you that it's somewhere here. It casts a shadow down on the plane, but now we have this line that points directly to our point. That is going to be what we call rho. There is, that would be r in the plane in cylindrical coordinates, but instead we use that reference line to measure theta, how far the point kind of sweeps from the positive x-axis. And then we also measure this angle downward from the positive z-axis, which is what we call phi. So you sort of figure out where you're facing. You swoop to which direction that is. You swoop down from the z-axis to phi, and then you go out from the origin a distance rho until you meet the point that you're interested in. So these 3 coordinates describe what is known as spherical coordinates. As you can predict, it's really nice for modeling spheres. What we would usually measure as a sphere in Cartesian coordinates would be the set of all points x, y, and z, such that their distance from the origin squared is some value a squared. So this is set of all points, a distance a from the origin. That's what a sphere is. It's an equidistant 3-dimensional set of points. We know that a distance in 3 dimensions can be written by taking the Pythagorean theorem and just adding a z² to that. Now we have 3 dimensions, but it still works out that it is equal to the distance. x² plus y² plus z² is equal to the distance from the origin, a². So that means if we want to write this in spherical coordinates, the quantity rho is just rho squared is just x² plus y² plus z² equals a², which allows us to take the root of both sides, and rho equals a also describes the sphere. It is much cleaner in this spherical coordinate system than in the Cartesian frame. If we want to do some conversions, we should first draw a special triangle to help us out here. This represents our hypotenuse rho. There is a vertical distance down that is going to represent z, the distance above the xy plane. And then there's this distance r from the origin out to the shadow of our point in the plane that represents r. So this r and this z are cylindrical, r and z, and they're related to this new coordinate rho in the following way. R is perpendicular to z. This angle here, from the actual z-axis down to our line rho, represents the angle phi. By an old geometric friend, alternate interior angles, this is also the angle phi. And so we can relate rho, z, r, and phi by this kind of triangle that emerges when you connect the line rho down into the plane. So we can get some conversions. Our r from cylindrical coordinates is thus going to be rho sine phi. R represents the opposite side of that triangle. And so the natural conversion with rho as the hypotenuse is r equals rho sine theta. That means that z is the adjacent side. It's going to be rho cosine phi. If x in cylindrical coordinates is r cosine theta, we can now substitute this r into this expression here and write in polar coordinates rho sine phi cosine theta. We also have the same for y, where we get rho sine phi sine theta. So in spherical coordinates, x and y are preceded by the same factor, rho sine phi. X takes its usual cosine theta to project that out, and y takes the sine theta. The z coordinate is just rho cosine phi. It doesn't match the other two, and there's no secondary angle in terms of theta here. So that's a kind of good way. X and y have the same r there. Z is doing its own thing. Pythagorean theorem tells us that rho is equal to the square root of the sum of our three Cartesian coordinates, x, y, and z, all squared. And this is also, if we're looking to convert between cylindrical and spherical, we can replace the x squared plus y squared with, you guessed it, r squared, and add the z squared on for good measure. And that's encompassed in this triangle here as well. R is a leg of a triangle, z is a leg of a triangle, so rho as the hypotenuse follows directly from Pythagorean theorem. We can look at ways to convert, again, nasty expressions in Cartesian into much simpler expressions in spherical. We're going to derive this. It's not going to look nice along the way, but the end result will be way much cleaner. So we have x squared plus y squared plus z minus 1 squared equals 1. This describes a sphere centered at the point 0, 0, 1. X and y are in their normal places. This z coordinate's been shifted over by 1, and so we've just taken our sphere centered at the origin and moved it up a notch. Well, we're going to take our conversions up here and substitute them into the Cartesian expression below. So look at this. We get rho squared sine squared phi cosine squared theta plus the same thing for y, but it's a sine squared theta at the end. Z, we're going to leave that in parentheses for now, but it's going to be rho cosine phi minus 1 squared equals 1. So one interesting thing, oh shoot, that should be a sign for the y coordinate. One interesting thing we can see here is that we have the same coefficient, rho squared sine squared phi times cosine squared, then sine squared. We can factor out the rho squared sine squared phi. We're left with a cosine squared plus sine squared, which is just 1. So this whole mess simplifies to rho squared sine squared phi plus, we can FOIL out this expression over here. We're going to get rho squared cosine squared phi minus 2 rho cosine phi plus 1 equals 1. We can cancel out the 1's on both sides of the equation, move the negative 2 rho cosine over, and then note that we have here another sine squared plus cosine squared with the same coefficient. So the sines and cosines go away, and we're left with rho squared equals 2 rho cosine phi. Rho equals 0 is a solution here. That's not very interesting, so we can cancel through by a factor of rho, and we end up with rho equals 2 cosine phi. So this is a much simpler expression than the one we started out with. Yes, we had to do a little bit of legwork to get there, but with a couple clever trig identities and some messy algebra, we were able to get this into a nicer expression, which this is going to be a lot nicer to integrate than all of this together. So that's the motivation here. We do a little bit of legwork up front. Algebra is easy, so that when we actually have to do the calculus later on, the calculus goes much smoother. Last thing to take a look at, well, two things really. One is that spheres are obviously a really nice thing to measure with spherical coordinates, but it turns out that cones are ideal for spherical. In Cartesian coordinates, a cone is described as a function z is equal to the square root of x squared plus y squared. If we substitute in our polar expressions, this is just r, so we get z equals r, which is the same thing as rho cosine phi equals sine phi times rho. The rho factor cancels out on each side, and we get an expression between the angles phi cosine equals sine. That happens for this particular function at pi over 4. That's when sine is equal to cosine, 45 degrees. And so what this is saying is the cone that we started with in spherical coordinates is just an angle. In other words, if this is my z-axis, we are measuring the set of all points that are some angle phi from that positive z-axis. We stop once we get to that angle, and then we rotate that line around. And what that generates is a cone. Different weights on the x squared versus the y squared will give you a different angle. So you could express different Cartesian cones, which are quite ugly, as a much more simple, what angle do I want the cone to be slanted at? I'm just going to have phi equal that angle, and I generate the cone. So that is a nice little trick. Spherical coordinates make cones. Who knew? So let's put it all together. Let's do one last conversion. We want to convert the Cartesian point. P is 5 and 2 other numbers. We want to convert to spherical. Well, we're going to use our conversions with the numbers that we have here. This is, again, x, y, and z. Rho is going to be equal to the square root of the sum of the squares of those three values. So we're going to add 25 plus 36 plus 49. If we add all those together, I get root 110. The angle theta is found by the usual y over x inverse tangent of that ratio. So here we're going to have inverse tangent of 6 over 5. Calculator tells me that is about 0.876 radians, or 50.2 degrees. Phi, on the other hand, if we go back to our triangle up here, phi is going to be the inverse tangent of r over z. So we do kind of have to do an interlude here to figure out what our polar r is, but that's just looking at x and y. R is going to be equal to 5 squared, 25, plus 6 squared, 36, all under a square root. So r here is the square root of 61. So we take that r value with the z value that's given to us, 7. We do tan inverse root 61 over 7. Not the nicest set of numbers there, but we can put that into our calculator and we get something like 0.84, almost exactly, radians. And that converts to an angle of 48.1 degrees. So if we want to express this point in polar coordinates, we usually do so in the order rho, phi, and then theta comes last. We get root 110 for phi. We get 48.1 degrees for the polar angle phi. No, sorry, it's not the polar angle. This is actually kind of a fun aside. Phi is sometimes called the azimuthal angle. So if you want to impress your friends, use that terminology. Theta is the polar angle, and that's the one that's 50.2 degrees. I didn't give myself much room. 50.2 degrees, end parentheses. So there you have it. This is just an intro to learning the two major three-dimensional coordinate systems. You will find that if you can master these, you will be very easily able to express and work in three-dimensional space.